Correlation in SPSS is a relationship between variables. Correlation is a measure of a relationship between variables. Whether this relationship is positive relationship with one variable increase, the other increase, or a negative relationship when one of the variable increase, the other decrease, or there is no relationship. So that is the essence of doing correlation. So statistical relationship between variables are measured by covariance to work out and calculate the correlation coefficient. So correlation test will produce a correlation coefficient, which is a measurement or a measure for the relationship between variables. Two variables are associated if they covary. Correlation will determine the direction of the relationship, whether there is an increase or a decrease. The strength of the relationship on a scale from +1 to -1. +1 indicate the strongest relationship and a positive relationship. -1 indicate a negative relationship and a strongest relationship. And 0 indicate there is no relationship. Also, when measuring the relationship between variables, significance of this association is determined. Now, there are several types of correlation. Bivariate correlation, pi mean 2, and variate variable. So it examines the correlation between two variables. Zero-ordered correlation is an example on it is a Pearson product moment correlation coefficient that is used when the data are normally distributed, and it is used for parametric data. For non-parametric data, Spearman's correlation coefficient or Spearman's ranked correlation coefficient, it's called abbreviated RAW, is also used for non-parametric data. A third option when the data are not normally distributed, i.e. non-parametric, is to use the Kendall's tau correlation coefficient. Another type of correlation called partial correlation. In partial correlation, it examines the correlation between scores of two variables while controlling the effect of one or more of additional variable on both variables, which is different from part or semi-partial correlation. It examines the correlation between two variables while excluding the effect of one or additional variable on only one variable of those two variables, but not both. So that is the essence of the difference between partial and semi-partial correlation. Now, when we do the test for correlation, you have choices either to go for significant test to test one-tailed test or two-tailed test. When the direction of the relationship between the two variables is known, whether it is positive or negative, then directional hypothesis can be used and one-tailed test can be used. So one variable increase, the other increase, or the other one variable decrease, the other decrease, then we go for one-tailed test. However, if we cannot predict the nature of the relationship, whether there is an increase or decrease, then it's safely to stick to the default two-tailed test. Now, before conducting correlation analysis, it is essential to plot, scatter plot, to look at a general trend of a data. Graph that plots each score on one variable against a score on another variable is called scatter plot. The plot will show the relationship between variables, whether there is a relationship or not. What kind of relationship? Is it positive? Is it negative? Or there is no relationship? Whether there is an outliers in your data. So there are several scatter plots to draw in SPSS. First one is simple scatter plot. Second one is 3D scatter plot. Third one is overlay scatter plot. And the fourth one is the matrix scatter plot. Simple scatter plot examines the relationship between two variables, as we can see here data 1 on the y-axis, data 3 on the x-axis, and the data are plotted, and we can see here there is a line that indicating a positive relationship between the two variables. In a 3D scatter plot, it displays the relationship between three variables on a 3D format, as we can see data 1, data 4, and data 7 plotted in one graph. Overlay scatter plot displays several pairs of variables on the same axis. Here, as we can see, we have variable 1 is plotted with variable 3 and variable 4. So one variable is fixed on one axis and the other variable 3 and 4 drawn on the other axis. So this shows an overlay of the pairs of variables. So we can see here the correlation between variable 1 and variable 3 and variable 1 and variable 4. Now matrix or matrix scatter plots allows examining the relationship between all combination of many different pairs of variables. If you have several or multiple variables and you want to plot them into pairs, you can do it in one diagram or a chart. It's called matrix scatter plots. It's convenient when you have multiple variables and you want to look at the correlation between them. Association between two variables can be examined by looking at whether they covary. What does covary mean? When one variable deviates from its means or its mean, the other variable deviates from its mean in a similar way. There is an equation to follow. Once you follow the correlation equation, it will produce in Pearson a coefficient called R, and the R is a covariate divided by the standard deviation for both variates or both variables or two variables. Now, the correlation test will produce a correlation coefficient, which is a measure of the relationship strength. A coefficient of 0 to 0.1 indicates no correlation. 0.1 to 0.39, weak correlation. 0.4 to 0.69, moderate correlation. 0.7 to 0.89, strong, and 0.9 to 1, very strong relationship. Now in this presentation and tutorials, I'm going to show you how to give you a few background on each test and explain it, and then show you how to do it in SPSS. So we're going to describe a few parametric correlation tests. The first one is the Pearson's correlation coefficient, or sometimes they call it Pearson's product moment correlation coefficient, and it's have an abbreviation called R. Another parametric test that will be described is the partial correlation. and a third one is semi-partial correlation, and then we will look at the point-biserial correlation and then biserial correlation. For the non-parametric test, I will describe and show you in SPSS how to do the Spearman's correlation coefficient, or the Spearman's ranked correlation coefficient, and the other one, which is the Kendall's tau correlation coefficient. Pearson's correlation coefficient, abbreviated as R, is, or sometimes it's called, Pearson's product moment correlation coefficient, is a parametric statistical test. So it only can be used on data that are parametric. The test measures the strength of a linear relationship between two variables that are continuous, such as intervals and ratio, and normally distributed. The test calculate and determine the correlation coefficient, the R, which is calculated by covariance of two variables divided by the product of their standard deviation. The test will determine the R value, the strength of the correlationship, or the relationship between the two variables on the scale of +1 to -1, as +1 the strongest positive increasing relationship, the -1 is the strongest negative inverse relationship between the two variables. Also, the test determines the direction of the relationship, whether there is an increase or decrease, and also will calculate and determine the significance of association, i.e. the p-value between these two bivariates. Before conducting correlation analysis, Pearson product moment correlation test, it is essential to plot the scatter plot to look at the general trend of the data and to make sure that the data follow and adhere to the assumptions for doing the test. So what are the assumptions for doing Pearson correlation coefficient? The data should be from random samples. The variables are continuous. Continuous mean a scale from 0, from 1 to 2 or 3 and so on up to infinite. Continuous can be interval or ratio variables. The data on both variables have to be normally distributed. The data contain paired samples, and there is independence of observations between the two variables. One of the criteria to do a Pearson correlation coefficient that there should be a linear association or relationship between the two variables, and that can be confirmed using a scatter plot. There should be no outliers in the data, because outliers can shift the distribution of the data and become not normal. Now, this is a correlation tables extracted from SPSS, and here we have 4 different variables. Data number 1 up to 4 correlated with data 1 correlated with one variable here, variable data 1 correlated with variable 2, 3 and 4. In the first column here, when the table shows that correlation between data 1 and data 1, i.e. self correlation, give you a coefficient of 1 because you're correlating the data to itself, and there is no significant p-value here. If we look at the correlation between data 1 and data 2, again the coefficient is 0.166. This is a weak and positive relationship between data 1 and data 2. However, the p-value is 0.126. So this association, though there is a weak correlation between data 1 and data 2, it is not statistically significant. When we look at data 1 and data 3, we can see here that the coefficient, or the R, is 0.551. This is a moderate relationship, and it is a positive relationship. Whenever data 1 increases, data 3 increases, and it is statistically significant as the p-value is less than 0.05. However, if we look at correlation between data 1 and data 4, the R is minus 0.722. That's a strong negative inverse relationship between data 1 and data 2, and it is statistically significant as it is confirmed by p-value. So whenever data 1 increases, data 4 decreases. So this is a negative correlation with statistically significant value. Now, drawing the scatter plot, here is a simple scatter plot, shows the relationship between the two variables. Here data 1 and data 3, and as we can see, there is a positive relationship, and the R is 0.51. And there is also association between data 3 and data 1. Whenever data 1 increase, data 3 increase. The next graph show an inverse relationship between data 1 and data 4, and the R is equal to minus 0.71, as there is a strong but negative correlation between data 1 and data 4. Increase in data 1 is associated with decrease. Increase in data 1 is associated with decrease in data 4. The final graph here shows that there is no correlation, as we can see here. The R is nearly close to 0, and there is no correlation between data 1 and data 2. So that is the significance of drawing scatter plot as a first step when looking at a correlation between two variables. Bivariate correlation. This is one of the statistical tests that can be performed in SPSS. Bivariate means two variants or two variables. The test looks for a relationship or association between two variables or two groups or two samples. The test that is used is usually Pearson correlation coefficient. The test is used when the data are normally distributed and the variables within the data or the scores within the two groups are normally distributed and are continuous. So it is a parametric test. This test is used to find the relationship between those two variables or two groups, measure the strength, how strong is it, from a scale of -1 to +1, as +1 is the strongest relationship, -1 the strongest relationship, but it's an inverse relationship, 0 as there is no relationship. So the test will measure the strength of the relationship, the direction of the relationship, whether one variable increase, the other decrease, or the one variable increase, the other increase, or there is no one increase, the other has no association with the first one. So the test will measure the strength, the direction, and the significance of this relationship. So Pearson's correlation coefficient will determine the strength of the relationship on the scale of -1 to 1, the direction of the relationship or the association, and the significance of this relationship. And the way to do that is, here I have a data in SPSS for 4 groups labeled as data 1 to data 4. And on these groups there are scores, and I want to find out the relationship between data number 1 with 2 and data number 1 with 3 and data number 1 with 4. The first step in doing a correlation test, such as Pearson correlation coefficient or a parametric test, is to look at the data through a scatter plot, to look at the data and to find out whether what type of association between them, the relationship, the strength of the relationship, the direction of the relationship. Scatter plot will allow looking at the direction of the relationship and whether there is a relationship or not, and whether there is an outlier or not. The first thing is to do a scatter plot. To do a scatter plot, click on the graph, legacy, display, and then scatter plot. I'm going to use simple scatter. Click on continue, reset this. I'm going to look at the scatter data between data number 1 and data number 2. And if I click on OK, a scatter plot is generated, and as we can see here from this plot, the relationship between data number 1 and data number 2 is not defined. So there is no association between data number 1 and 2. When data number 1 increases, there is a random increase and decrease on the data. So here I can fairly say that there is no relationship between data 1 and data 2. I can confirm that by doing a correlation test using Pearson's correlation coefficient. The way to do that is to click on Analyze and then scroll down to Correlate, and then go for Bivariate. Click on Bivariate, reset this. In this Bivariate, I'm going to correlate between data number 1. So I'm going to move data 1 into variables box, and then I'm going to also transfer data 2 into the variable box. Here I'm going to select the Pearson coefficient for correlation, or correlation coefficient, and I'm going to ignore the Kendall's 2B and Spearman correlation, as I'm going to describe this in a separate video or separate videos. And since we don't know the relationship between this data, so we always safe to stick to test of significance for two-tailed. However, if I know that data 1 and there is association between data 1, which is increase or decrease, I can choose a one-tailed significant test. But here I'm going to stick safely to as a default for two-tailed significant test. And I'm going to flag the significant correlation. If I click on options, it's not a lot of to choose, but I might select mean and standard deviation. If I want to look at how the mathematical calculation of the Pearson coefficient, I can select the cross product deviation and covariance, but I'm not going to select that. Click on continue. And scale and the style, I'm not going to make any changes. If I click on OK here, what happened here, as we can see, this scatter plot shows that there is no association whatsoever between data 1 and data 2. Pearson correlation coefficient has been calculated using SPSS. In the first table, we see here that the data, the mean and the standard deviation for each. And in the second table, we see a correlation between data number 1 and data number 2. Again, as we say here, if we compare data 1 to data 1, of course it will be, the correlation will be perfect, and the value for the correlation coefficient will be 1, which is the maximum strength, because you're comparing the data to itself and there is no significant. And as we can see here, the number of the data are 86 scores. Now if we compare data 1 to data 2, we can see here that there is a minus 0.08. that indicates there is a small inverse relationship, minor inverse relationship between data 1 and data 2, but again it is 0.01. so this is really very, very, very low, and it's even, there is no significant, we can consider there is no correlation between data 1 and data 2. This is backed up by the p-value, as the p-value here is 0.45, which indicates that it is really not significant. So here we can safely state that data 1 does not correlate with data 2 at all. So there is no significant association between data 1 and data 2. So that's for data 1 and data 2. What about if I want to compare data 1 to data 3? Again, I'm going to repeat the same thing. Draw a scatter plot. Going to move data 1 to y-axis, data 3 to x-axis, or vice versa. If I look at the diagram here, scatter plot, I can see here that there is a fairly positive relationship between data 1 and data 3, as there is an increase when data 2 increases, data 1 increases. So there is an indication that there is a relationship between those data. To confirm that through a statistical analysis, I will do a Pearson correlation test. So if I click on data, again repeat the same step, keep the same thing as before, click on OK. Here again correlation table is generated. And now if we compare data 1 to data 3, we find out that there is a correlation coefficient, or we call it here the R. The R, Pearson correlation coefficient is called R, and the R is 0.55. That is really a moderate relationship. And the sign here is positive, so there is a positive relationship, which means that when data 1 increases, data 3 increases. And this association is extremely significant, as the p-value is less than 0.05. So there is a strong correlation, as we can see here from the scatter plot and from the statistical test using Pearson's correlation coefficient, that there is association, a positive association between data number 1 and data number 2, and this association is statistically significant. Now if we move again to try to compare data number 1 with data number 4, repeat the same thing again. Scatter plot, remove data number 3 from here, replace it with data number 4, and hit the button for OK. Again, from the scatter plot comparing data 1 with data 4, I can see here the inverse relationship. When data 2 increases, when data 4 increases, data 1 decreases. When data 4 increases, data 1 decreases. So there is an inverse relationship. To confirm this, you need to do a statistical analysis. The way to do that, to go to correlation, Bivariate, reset that. I'm going to select compare the data between data number 1 and data number 4. I'm going to keep everything as before. Again, here the correlation says that there is a correlation between data number 1 and data number 2. As we can see here, the value for R is minus 0.722. which indicate that this is an inverse relationship between data 1 and data 4, and in a sense it's minus, and the relationship is really strong as it is 0.7, and it is significant at the p-value for the statistical test, and the association is really below 0.05. So that graph, scatter plot graph, and the Pearson correlation coefficient indicate that data 1 and data 4 are associated, and they are in fact negatively associated. There is an inverse relationship between them, and this relationship is really strong. You can call it a strong relationship, and it is significant. So this is the way to do correlation and or association test between two variables. Look at the scatter plot and then backed up that with a statistical test for Pearson correlation when the data are normally distributed and continuous. And Pearson will inform you whether the data are positive or negative, the data correlate to each other positively or negatively, whether the correlation is significant, and the strength of this correlation or length or association.
Partial correlation. Partial correlation is a correlation between two variables in which the effect of additional 1 or 2 or 3 or 4 variables, in this case they are called covariates or controlled variables, the effect of those variables, whether it's 1 or 2 or 3 or more, are held constant and controlled when we do the correlation between those original two variables. So you have two variables and you have a covariate, and you will control or remove or exclude the effect or the influence of those variables on the original two variables. Then this is test done in this case is called partial correlation. The test measured using Pearson product moment correlation coefficient. It does measure the strength and the direction of a linear relationship between two variables. Thus it is considered here to be two variables, so it's bivariate. To do the partial correlation coefficient test, or to determine the coefficients, the data has to fulfill certain criteria and assumptions. There should be a linear relationship between all variables, between the two variables and between all variables. So you have to have a linear relationship. The variable should be continuous, scale, such as intervals or ratio or a number from 0 up to 0 plus 0 up to infinite. Normally distributed data. Those two variables are normally distributed. Has to be checked in advance before doing the partial correlation test. There should be no outliers in the data. There should be a similar spread across range, and the covariate should be continuous scale. Fulfilling all this assumption will permit doing the partial correlation test. Partial correlation is a parametric test, and partial correlation is used when you have two variable number 1 and variable number 2, and you want to correlate and find the relationship between variable number 1 and variable number 2, at the same time control the influence or the effect of a third variable or a fourth variable or a fifth variable on the effect on one of these variable, all of these variable on variable number 1 and 2, so on both variable. So the test to use is partial correlation, and this test is used when the assumptions are fulfilled. The assumption is that the variables 1 and 2 or variables are continuous, the variables are normally distributed, the variables have no outliers, the variables also has a linear relationship between each other. So the objective of this partial correlation test is to look for and examine the relationship, the strength of the relationship and the direction of the relationship between two variables, whether the relationship is positive or negative on the scale of -1 to +1, and the strength of this relationship and the direction and the significance of this relationship using this partial correlation. And partial correlation in fact uses Pearson correlation coefficient as described in my previous video clips. And the way to do partial correlation, here I have in SPSS a data here in labeled as data number 1, data number 2, and data number 3. And in these data I had already checked that the variables are normally distributed, data 1, 2, and 3, and they are continuous, and they all fulfill the assumption to do correlation and partial correlation. And in this example I want to compare the relationship between data number 1 and data number 2, and keeping the or removing the influence and the effect of the data 3 on relationship between data 1 and data 2. And the way to do that is to click on analyze and then scroll down to correlate, and then scroll down to partial correlation. And I'm going to reset this. Now in this box in SPSS, I had here to make sure that I move the data into the right box. So I want to compare data 1 with data 2. So these are the two data I want to find. I want to find the relationship between them, and I mean at the same time I want to exclude the effect of data number 3 on variables number 1 and 2. So the relationship between these two, excluding the effect or the influence of data number 3 on both data 1 and 2. And in this also I want to go for two-tailed test of significance, and I want to display the actual significant level. And if I click on options, I want also to take the zero order of correlation. Zero order of correlation will look at the correlation between all the three variables without partitioning the relationship. So if I click on continue and then click on OK, an SPSS will generate an output for correlation coefficient. Again, if you notice here at the bottom, it says cells contain zero order Pearson correlation. So here in this statistical analysis, Pearson correlation coefficient was measured and calculated for ordered zero order and for partial correlation. So the table is two sections. The top section which indicate none, which means there is no controlled variable. So all the variables has been correlated with each other without controlling the effect of data 3 on 1 and 2. However, in the bottom section here, data 3, as it's indicated here, has been held constant. So its effect has been removed and their correlation was calculated between data 1 and data 2 without data 3 in consideration. Now, if we go back again here and look at the correlation between data 1 and data 2 and data 1 and data 3 without controlling any variables, we see that there is a relationship between data 1 and data 2. The relationship is positive, and it is moderate relationship, as it is 0.551, and the association between those two data are significant, as the p-value is less than 0.05. When also look at correlation between data 1 and data 3, we see that there is a correlation, a positive one, but weaker. It is 0.376 compared to 1 and 2, and there is a strong association, a significant association between data 1 and data 3. Now, if I remove the influence of data 3 in both, I will look at the correlation between data 1 and data 2. Data 1 and data 2, when controlling data 3, we can see here that the correlation between 1 and 2 is still positive, still statistically significant, but it increased from 0.55 to 0.57. So there is a slight increase in the correlation between data number 1 and data number 2 when the data number 3 is held constant and its influence was removed in both compared data 1 and data 2. So this test is really designed to correlate between two variables, controlling the effect of a third or a fourth or a fifth variable or variables on the original variable number 1 and number 2.
Part correlation or semi-partial correlation. Either it's called part correlation or semi-partial correlation. This correlation type of correlation is different from partial correlation. I've had already made a video clip describing partial correlation. In this one, I'm going to describe the semi-partial correlation or part correlation. It's a test used to find out correlation between two variables in which the effect of a third variable is only controlled on one of the variable, i.e. if you have two variables, variable number 1 and variable number 2, and you want to do a correlation between variable number 1 and variable number 2, at the same time you have a third variable and you want to exclude the effect of the third variable on only either the variable number 1 or the variable number 2, but not both. If it is both, then it is partial correlation. Semi-partial correlation, the effect of the third variable is held constant on only one of the variables. So the test uses regression analysis to calculate the coefficient. And for a data to be used to analyze it and find the correlation, it has to fulfill certain assumptions and criteria. You need to make sure that your variables are continuous variables. The three variables are continuous variables, which mean intervals or ratio. Those variables are normally distributed. You need also pre-doing the analysis to plot a scatter plot to look at the linear relationship between all variables. So linearity of the relationship is and important factors. And those variables, there should be no outliers, and the variables you want to hold constant can be one or more than one. Semi-partial correlation, or in another word, part correlation. Semi-partial correlation is different from partial correlation. I have already described partial correlation between two variables in a separate video clip. Here in this video, I will only describe how to do semi-partial correlation or part correlation. This correlation test is a parametric test. The test examines the correlation between two variables when the effect of a third variable is held constant or removed on one of the variables, one or two. So if you have one variable compared to another variable 2, and you have a third variable, then you correlate variable 1 with variable 2 and remove the effect of variable 3 on one of the variable, either variable 1 or variable 2. To do the test, the data has to be normally distributed. The data has to be continuous. The data has to have a linear relationship. Variable 1 and variable 2 have a linear relationship, and there is no outliers in the data. So the way to do it in SPSS, here I have three different variables labeled as data 1, data 5, and data 6. And I want to do a semi-partial correlation between data number 1 and data number 5. And at the same time, I want to hold the effect of data number 6 constant on one of the variable, in this case on variable 6. So the way to do semi-partial correlation is to click on Analyze, and we are going to use regression analysis to perform this parametric test. Here in this box, I am going to move the data into the dependent variable, and I'm going to correlate data with data 1 with data 5, and move also data 6 into the independent. So data 5 and data 6 will be an independent variables. Move them to the independent variables. On the statistics box, I'm going to take on a box that say part and partial correlation. So the software will calculate both the part and partial correlation, and I click on OK. Plot, I'm not going to make any changes, and options, no changes. Here what I'm asking the computer software and the program in SPSS to correlate data 1 with data 5, and at the same time remove the effect of data 6 on only data 5 and not on both 1 and 5. So if I click on OK, the SPSS will generate an output, and in this output, regression outputs, the most important table is the table labeled correlation. Again, and toward the end here we have in the table the correlations coefficient using zero order, partial correlation, and part correlation. For our topic today, this is the important part of the table. In this table, we can see that correlation between data number 1 and data number 5, when we remove the effect of data 6 on data 5, or holding the effect of data 6 on 5 constant, the association between data 1 and data 5 is minus 0.605. So there is a negative relationship, and this negative relationship is moderate, and it is significant as the p-value is less than 0.05. So this table has calculated the correlation coefficient, part correlation coefficient for variable 1 and variable 5, holding variable 6 effect on 5 constant. For correlating variable 1 with variable 6, meanwhile holding the effect of variable 5 on 6 constant, the correlation coefficient was calculated and it is 0.174. This is a weak positive correlation, though it is statistically significant as the p-value is less than 0.05, and it is 0.023 here. So correlating data semi-partial correlation between data number 1 and data 6, controlling the effect of 5 on 6, the coefficient value is 0.174. So in this way, I had shown you how to do semi-partial correlation between two variable 1 and variable 5, simultaneously controlling the effect of a third variable on only one of the variable 5, not variable data 5 and not data 1. Again, the same thing here, semi-partial correlation between two variable number 1 and variable number 6, and holding the effect of variable 5 constant or constant, or removing the effect of variable 5 on 6 but not on variable 1. So this is the way to do semi-partial correlation between two variables simultaneously holding the third variable effect constant on one of the variables. Point-Biserial correlation coefficient, abbreviated as RPP. In fact, there are two tests. One of them is point-biserial correlation coefficient, and the other one is biserial correlation. So in point and biserial correlation tests, one of the two variables you want to find the correlation between is dichotomous. Dichotomous means that it is binary, categories, two categories, such as pregnant or not pregnant, yes or no, dead or alive. Dichotomous variable can be discrete or continuous. Discrete dichotomous variable such as dead or alive, pregnant or not, yes or no. Continuous dichotomous variable such as fail, pass, or fail marginally. So there is underlying continuity. So that's why it is called continuous dichotomous. So there are two tests: point-biserial correlation coefficient, in which one of the variable is discrete dichotomous and the other is continuous variable. However, in biserial correlation coefficient test, one of the variable is continuous dichotomous and the other is continuous variable. So that is the difference between those two tests. the Point-Biserial correlation coefficient. Calculate the correlation coefficient between two variables. One of them is discrete dichotomous and the other one is continuous variable. Biserial correlation, calculate the coefficient between one variable that is continuous dichotomous and another is continuous. So for Point-Biserial correlation coefficient, it is a parametric test. It is based on or uses the Pearson's product moment correlation. It does measure the relationship between two variables, the direction of that relationship and the strength, whether it's and the strength. An independent t-test can be also used to calculate some of the parameters in the test. For data to be used and for Point-Biserial correlation coefficient to be calculated, the data have to fulfill certain assumptions and criteria. There should be one continuous variables, and in that continuous variable there is no outliers. So it means that it should be normally distributed for both categories. When you split the continuous variable between the two categories, it is normally distributed. And there should be one discrete dichotomous variable. And one of the also prerequisites for the test is that you have a homogeneity of variance for each dichotomous variable. The data in each of the dichotomous variable has a homogeneity of variance. I've already explained what is a homogeneity of variance in a separate video clip, and it's already on the channel. Again, there is no outliers in the data. Now, this is a scatter plot for a dichotomous data, for a dichotomous group. So two categories, male and female, and the score. Again, as you can see, there is and we draw a line. As we can see, there is, once you shift from male to female, there is an increase in the score. So that is where how to use the Point-Biserial correlation coefficient to look at two categories and the correlation between the two categories when one of the variables is dichotomous and the other one dichotomous discrete and the other one is continuous, which is the score. And you build up or establish a relationship, try to establish a relationship between those two variables through looking also at the scatter plot. The scatter plot shows that the male score is there is an increase once you move from the male to female, an increase in the score. Point-Biserial correlation coefficient is one of the statistical tests that can be used to examine the relationship between two variables. One of these variables is discrete dichotomous, which means it is two categories. Dichotomous mean two categories, like yes or no, life or dead, pregnant or not pregnant. And the other variables is continuous, whether it is a ratio or intervals, but it is continuous and it has to be normally distributed and lacks outliers. So the test will examine the strength of the relationship, the direction of the relationship, and will determine the significance of association between the two variables by producing a p-value. So the Point-Biserial Point-Biserial correlation coefficient in fact is based on using the Pearson correlation coefficient. So it is considered to be a parametric test. And the way to do that in SPSS, here in this data view, I have two set of data, two variables. One is labeled gender, the other one is labeled score. The gender is from 1 to 2. 1 is representing male and 2 representing female, as clearly shown here in the value. And as we can see here that the gender is a category, so it's nominal, it's either male or female. The score is numerical, so it's a scale from 0 to 100. And in this example, we want to do a statistical test to determine whether there is a relationship between the gender and the score, and find the correlation and the correlation coefficient. For this type of data, since we have here a dichotomous, discrete dichotomous variable which has two categories and a continuous variable, then the way to do that is to use the Point-Biserial correlation coefficient based on Pearson correlation coefficient. To do that is to click on Analyze, scroll down to Correlate, then click on Bivariate. Pi mean 2, variate mean 2 variables. Here in this window, I'm going to look for correlation between gender. So I'm going to move the gender to the variables, and I'm going to move the score to the variables. In the options, and I'm going to also tick the statistics for means and standard deviation. Click on Continue, and I make sure that the correlation coefficient here we use is the Pearson for this data to test. And I will stick with the two-tailed test of significance to get a p-value. And if I click on OK, here in this output of SPSS, we have two tables. The first one is descriptive, showing the mean of the scores and the number of cases. As we can see here, 86 cases. The second table is the correlation coefficient, correlating the data of the gender with the score. Again, as we can see here, there is really a strong statistical association between gender and score, as the value, the R value is 0.87, and this is really a strong relationship, and it is a positive relationship. And the statistical significance, the p-value is less than 0.05. So here we can clearly see that there is a clear association between the gender and the score, and it is statistically significant, and the correlation is positive. To understand better the meaning of this table, I'm going to draw a scatter plot to look at the data, and the diagram of the scatter plot will, from it we will determine the correlation between the gender and the score. So if I click on the graph here and I scroll down to legacy and then to the scatter dot, I'm going to select the symbol scatter, and I'm going to click on define. I'm going to put the gender at the x-axis and the score at the y-axis. And if I click on OK, a scatter plot will be generated. As we can see here, it's 1 that represent male, 2 represent females, and the y-axis is the scores. Again, as we can see here, that the scores increases, or the female have a higher scores than male scores. So there is a higher proportion of females score compared to male. I'm going also to double click on this graph. I'm going to add to it trend line, and as we can see here from the trend line, if I just untick the this label and click on apply, and then shrink this, and then shrink this, close this. Again here the output has, SPSS output has drawn a line here to represent that there is a linear relationship between gender and score, and the more the gender moves from male to female, there is an increase in the score, and this relationship is a positive relationship and a significant relationship of, as we determined here, 0.88. So this is the way to do a correlation between two variables. One of these variables are discrete dichotomous and the other one is continuous variable. The way to do that is to do a point-biserial correlation coefficient based on Pearson equation or Pearson method. Biserial correlation coefficient RB is different from point-biserial correlation coefficient. I have already described the point-biserial correlation coefficient in separate video. So need to make sure that there is no confusion between the both tests. There is a difference between both tests. In this video, I will describe the biserial correlation coefficient. It is a parametric test, and it is based on the Pearson's product moment correlation. It does measure the relationship between an ordinal variable and a continuous variable. So you have one of the variable continuous, the other one is ordinal. It calculates first the point-biserial correlation coefficient RPP, then uses the equation below to determine the biserial coefficient. The RP equal to point-biserial correlation, the RPP, multiplied by square root of proportion of cases in category 1, proportion of cases in category 2, divided by the ordinate of the normal distribution. And shortly I will show you how to use this formula. To use this test, the data has to fulfill certain assumptions and criteria. The data has to be normally distributed, i.e. normal distribution of the continuous variable, homogeneity of variance for both variables. I have already described homogeneity of variance in separate video clip, and also a continuous dichotomous variable. So you have two variables, one of them is continuous, the other one is ordinal, or it is a continuous dichotomous variable. So these are the conditions that if they exist, then biserial correlation coefficient can be used to calculate the correlation between those variables. One is continuous dichotomous and the other one is continuous variable. Now, table of standard normal distribution will be used in this test to work out the y ordinates. So the P1 and the P2 can be calculated from the data, and I will show you shortly how to do that. Once you obtain the proportion 1 and proportion 2, use this table of standard normal distribution to find out the y ordinate for these large proportion and small proportion. Biserial correlation coefficient is one of the statistical tests in SPSS that can be used to measure the relationship between two variables, two groups of data, two set of variables. One of the variables is continuous variables and it is normally distributed variable without an outliers. The other variables is dichotomous, i.e. categorical, but dichotomous with continuity, so it's called continuous dichotomous. An example of that: fail and pass. Failed, anything, any grade, any mark of 60 plus, it is pass. Anything below 60, it is fail, and fail can be fail marginal. So this is a dichotomous variable with underlying continuity, and if we want to compare and find the relationship between those two variables, one of them is continuous, the other one is dichotomous, continuous, dichotomous, or ordinal, the test to use is biserial correlation coefficient. In fact, biserial correlation coefficient works by determining first the point-biserial correlation coefficient, which I've already described in a previous video clip. Once the value, the R value for the point-biserial correlation coefficient is determined, a formula given below can be used to work out and calculate the biserial correlation coefficient. And the equation states that the coefficient for biserial equal to the coefficient of point-biserial multiplied by the square root of P1 and P2. P1 is the proportion of cases in category 1, or the percentage. P2 is the proportion of cases in category 2, divided by an ordinate y. Y is an ordinate of the normal distribution, and this value can be extracted from a table of the standard normal distribution table following a standard normal distribution curve. So to do this test in SPSS, I have here a data sorted out in two columns, two variables. One of them success, pass and failure, as you can see here, pass and failure. And this success or failure is a dichotomous, as I have labeled failed 1, 2, pass. And it is an ordinal, as success is just categories and the score is numerical. So the success, pass and fail with marginal failure and or the ordinal dichotomous. This is a dichotomous or ordinal dichotomous variable, and the score is a continuous variable from 0 up to 100, and I've checked that it is normally distributed without an outliers. To find out if there is a correlation or relationship between this dichotomous variable, continuous dichotomous variable, with this continuous variable, first of all we have to calculate the point-biserial coefficient, and point-biserial coefficient can be calculated using Pearson correlation coefficient. I've already described that also in a separate video for how to do Pearson correlation coefficient.
The way to do the analysis and test is to click on Analyze, scroll to Correlate, Bivariate, as pi stands for 2, variates mean 2 variables. If I click on bivariate correlation, I have here a box. I'm going to correlate between the success, which is the dichotomous variable, with the score, which is the continuous variable. And I'm going to keep the tick for correlation coefficient for Pearson. Pearson correlation coefficient to calculate the coefficient for the Point-Biserial. And I'm going to stick with the two-tailed test of significance as shown here. And if I click the OK icon, I get this table. This table shows that there is a correlation between success and score. And the value for the correlation is 5.504. So this is really a moderate relationship between those two variables, the dichotomous one and the continuous one, dichotomous and the continuous variable. And in fact, there is a strong, significant, and this is really, this relationship has a significant value of less than 0.05. So this is really credible and statistically significant relationship between success and score. The value for this in this table can be considered as here Point-Biserial correlation. And then now we need to calculate the biserial correlation RB. And to calculate the RB, we are going to use the formula here given below. As we can see here, the RB is already determined to be 0.504. Now I need to determine the P1 and the P2. To determine the P1 and the P2, the way is to click on Analyze, Descriptive, Frequencies, Reset, and then I'm going to find the proportion or the percentage of pass and failure. So I'm looking at the dichotomous variable, and I'm not going to make any changes here, just stick to this and click on OK. In this table here, success and failure, it's a fail and pass. So there are 58.1% fail and 41.9% pass. So the proportion here is 0.581 for fail, 0.419 for pass. So I'm going to use this value to and apply them into the standard normal curve table here. As you can see, large portion, small portion. So our first p-value from this table here we've shown is 0.581, and the other one is 0.419. So we need to use these two values on this table here. If we look at the larger portion here of 0.58, if we scroll down from 0.581 up to here, I have labeled this value with a red square or rectangle, and this is the value 0.581 closest to 0.581, and then for the smaller portion 0.419, the closest one is here. So from this coordinate we can calculate the y, and the y here is 0.3902. This is the way to work out the y ordinate from that standard table using a larger portion and a smaller portion, P1 and P2. Now I need here to use a calculator. So if I click on calculator here and back again to statistics and the calculator, so what I'm going to use the formula. First of all, I'm going to put the value for calculate first the portion 1 and portion 2 multiplied, then square root of it. So the P1 is, as we can see here, is 0.581 multiplied by 0.419 9. If I hit equal, this will be 0.243 and so on. If I do a square root for this value, now I've got the square root of proportion 1, proportion 2. Then I need to multiply that by the coefficient of point-biserial following the equation. The point-biserial is determined here is point, so multiplied by 0.504. Hit the bottom equal, so I still get 0.248. And I need now to divide that by the y-ordinate, and the y-ordinate is, as I've already calculated, that is 0.3902. And if I click OK, then this is the value for the Pearson biserial correlation coefficient 637. This value, as we can see here, the biserial correlation coefficient is 0.637. The point-biserial coefficient is 0.504. So this is higher. The value for this is higher than the point-biserial. So this is the way to do and measure and calculate a relationship or a link or association between two variables. One of them is continuous variable, normally distributed. The other variable is dichotomous variable when there is an ordinal in it, i.e. there is continuity of it. The way to do it is to do a biserial correlation coefficient following the formula given, using two tests, the Pearson correlation coefficient and the point-biserial correlation coefficient, to work from them to extract the point-biserial and then use the equation to determine the value for the coefficient for the biserial.
Spearman's correlation coefficient, abbreviated as ρ. It is a non-parametric statistical test. So a test that used when the data are not normally distributed. So it does measure the strength and the direction of association between two variables, two non-normally distributed variable or two ranked data. The test arrange the data into ranks, then uses Pearson equation to calculate the raw value. It can be used for correlation between Likert scale items. The test determines the raw value for a correlation between two variables and determine the strength of the correlation on a scale of -1 to +1. +1 is the strongest correlation, -1 is strongest correlation, but it is inverse. +1 is strongest correlation, but it is a positive relationship. So it tells the direction of the relationship, whether the relationship or the correlation, whether there is an increase or an inverse value. It does determine also the significance of this association by producing a p-value. Now, to do the test, the data has to fulfill certain requirements and assumptions. The data has to be random. One variable is ordinal, the other is continuous, or both are ordinal, or two variables that are continuous but they exhibit monotonic relationship. The data contains paired sample or samples, independence of observation, data are not normally distributed, and ranked data. So the test is used for non-linear relationship, i.e. monotonic relationship between two variables. And it is a non-parametric test for the data that are not normally distributed or ranked or ordinal. Bivariate correlation. Spearman's correlation coefficient is a non-parametric test, is one of the tests available to look for and examine relationship between two variables or two groups or two samples. When the scores within one of the variable or one of the group is not normally distributed, then you cannot use a parametric test like Pearson's correlation coefficient. Spearman's is the one to use when you have one of your data are not normally distributed. In fact, one of the conditions for Spearman's correlation coefficient is that one of the data need to be ordinal. Ordinal means non-parametric, means that the data are in order like A, B, C, D, E, F. So this is called ordinal. The second variable can be continuous or can be again ordinal. So Spearman's correlation coefficient is a test for finding out the relationship, association, link, correlation between two set of data and two variables or two variables. The test well measures the strength of the association by assigning a factor or a value called RHO coefficient. If the value is -1, then that means the strength, that's the strongest correlation, and minus indicate inverse relationship. One variable increase, the other decrease. And if the rho coefficient is +1, then it is a positive relationship. One variable increase, the other increase. If the RHO or the coefficient close to 0 or 0, then it means that there is no correlation between two variables and there are no link. So the test really measures the strength of the correlation, the direction of the correlation, increase or decrease, and the statistical significance of this correlation. The way to do that is in SPSS is to look at this example. I have here 4 columns or 4 variables from grades, study hours, variable 1 and variable 2, I call them. So I need to find whether there is a correlation or a relationship or a link between grades that the student obtain from and correlate that to the study of hours, and then a variable 1 and a variable 2. Again, grades means 1, 2, 3, 4 indicate A, B, C, D, E, F. Give them a labeling. So the variable in the grades are ordinal. It is not normally distributed. It's not a continuous. The study hours also is a continuous because it can be 1 hour, 2 hour, 3 hour, 4 hour, 5 hour, 6 hour, 12 hours, 13 hours, and so on, 15 hours of study. Variable 1 also is a continuous, and variable 2 is a continuous. I've already checked the distribution of these data. Again, here I want to correlate the association between those variables and to find out whether there is link between them and what kind of relationship. Is it increasing, decreasing, and is it significant or not significant? For this test, for this data, we are going to use a test that is non-parametric. It's a Spearman's correlation coefficient. If I click on analyze, then correlate bivariate, go for bivariate correlation, and I'm going to move the grades to the variables section, the study hours to the variable section, and then variable 1 and then variable 2. Here in the coefficient correlation, I am going to untick the Pearsons because I'm not going to use the Pearson, because here our data are not normally distributed. One of the variable or the group are ordinal, so we cannot use Pearson. We only can use Spearman, and Kendall also probably can be used, but not in these circumstances. I will have another video describing when to use the Kendall to association or correlation test. Regarding the test of significance, since we do not know the relationship between studying and the grades, whether it is positive or negative, so we will stick with the default test of significance, two-tailed significance. However, if I know the relationship, whether it's positive or negative, then I can take one-tailed. But in this case, in our current case, we use the two-tailed. I'm going to keep the flag significant correlation ticked on. If I click on OK, a table will be generated as we see here and labeled as correlation. What does the correlation do here? Here, what's in fact done is that the Spearman's test took the data from column number 1 and column number 2, and column number 3, and column number 4, and put them in ranks, sort them out in ranks, and then used the Pearson correlation coefficient to find out the correlation or the association. So in this finding out here, it is calculated, the Spearman row calculated, looking at the grade, the relationship between the grade and study hours, variable 1 and variable 2. Again, if we correlate grades with grades, you will get a perfect relationship 1, which is the maximum, which is perfect. However, without giving statistical, because you are correlating the variable to itself. When we correlate the grades with the study hours, we can see here that we have a value of 0.45 and a positive value, which means that there is a positive relationship between number of study hours and the grade achieved. So if there is increase in the number of study hours, there is an increase in the grade, overall grade achieved. So there is a positive increasing relationship between these two variables. And the statistical significance is really less than 0.05. So there is a statistically significant correlation between the grades and the syllabus and study hours, and this is very significant at the two-tailed significance as indicated here. So the grade is associated with the study hours and linked to the study hours, and it is significant and it is positive. However, when we compare and correlate the grades with variable 1, we get here a positive correlation, which is a weak positive correlation, 0.156. So there is a correlation between grades and the variable 1. However, it is this correlation or this association is not statistically significant, as the p-value is 0.12. So in this case, I can safely say that there is a weak correlation between grade and variable 1, but it is not significant. So we cannot really rule out the relationship between grades and variable. Again, the same story if we look at and correlate between grades and variable 2. We get here a raw value of minus 0.046, which is very, very close to 0. However, it is minus. So there is an inverse relationship and a minus, a minus. So it's really slim correlation between grades and variable 2. However, the statistical significance and the p-value has shown that it is 0.65. So it is not statistically significant, as the two-tailed significant value was 0.65. and it is greater than 0.05. So thus here we can safely state that the correlation between there is no correlation between grade and variable 2, as there is the statistical significance, there is no statistical significance between this correlation, and the value for the rho is very low and close to 0. So again, here we can see from this example the correlation between variables, two variables, can be either positive or negative, statistically significant and not statistically significant. So the rho can tell you really the direction of the relationship, the strength of the relationship, and the significance of the relationship. Again, here also, if we look here, the other side, it's cross correlation between these variables. And if we look at Spearman's correlation with study hours with variable 1 and 2, again there is a weak correlation, 0.05 close to 0, and with variable 2 close to 0, statistically significant 0.6, 0.8, so there is no statistical significance comparing these two. If we compare variable 1 again, it's with variable 2, we can see it's 0.01 and it's 0.9, so there is no statistical significance between those variable 1 and variable 2. So this is the way to look at correlation between two data, two variables, two groups that have scores in them or data on them that one of these groups are not normally distributed, i.e. ordinal, and the other variable either ordinal or continuous, is through using the Spearman's correlation coefficient. Kendall's tau correlation coefficient is a non-parametric correlation test, and it is used to measure the strength and the direction of association between two variables. It is an alternative test to the non-parametric Spearman's rank order correlation coefficient. It is used when you do have a sample size that is small, or you have many tied ranks, which means many scores have same ranks. It is used for better estimation of correlation in population. The test can be used for analysis of Likert scale data. To use the test, there are certain criteria and assumptions that have to be fulfilled to use the test. And the first assumption is that the two variables you have, they can be either two continuous variables with outliers, which means they are not normally distributed, or two ordinal variables. The relationship between variables are not linear. It is a monotonic relationship. Kendall's tau correlation test is a statistical test that can be used to find out a correlation or association or a link between two sets of data, two groups of data, or two variables. And those variables can be either ordinal, in which the data are in order, like A, B, C, D, E, F, or ordinal with continuous. One of the variables is ordinal, the other is continuous, but it is not normally distributed, i.e. there is an outlier in the data, whether an extreme value or a low value. So the test is done or carried out or used when the data are not normally distributed. So it is a non-parametric test. The test also can be used when you do have a small data. You have two groups that have small values in it. The numbers are really small. So then Kendall's the one to use. How to do the test? We'll show you in SPSS. Here I have 4 variables. The first one is labeled ordinal, as it goes from 1 to 6, indicating A, B, C, D, E, F. So A for 1, B for 2, C for 3, and so on. And then there is variable 1, variable 2, and variable 3. Variable 1 is again a ordinal data, as it is 1, 2, 3, and variable 2, 2, and 3 is also a continuous variable. So again, as we can see here, we have a small number of data, 30 cases, and we need to find if there is a relationship between these 4 different variables. And the test to go for is Kendall tau correlation test, as we have here small number of data, small samples, two variables are either ordinal or continuous, that are not normally distributed. And to do the test, click on analyze, scroll down to correlate, click on bivariate, which means bivariables, 2 variables, and I'm going to compare the ordinal with all the 4, ordinal with all the 3 other variables. If I move them into the box under variables, and I'm going to use here the Kendall's tau correlation test, and I'm going to untick Pearson and tick the Kendall's tau test. For the test of significance, I'm going to keep it as two-tailed, a default test, two-tailed statistical test. I only can use one-tailed if I really know the direction of the relationship, whether there is an increase or decrease. Then we can use one-tailed test of significance. And then I'm going to take flag significant correlation. So this test will measure the strength of the correlation between 2 variables, whether it's strong or weak, positive or negative. As it will give a value from -1 to +1. -1 indicate very strong negative relationship. One variable increase, the other decrease. +1 is a positive relationship, which is a strong one. One variable increase, the other increase. When it's the value for the correlation is 0, then there is no correlation. So that test will calculate and determine the strength of the correlation, the direction of the correlation, and the statistical significance of this correlation. I'm not going to change anything in the options. Key is the same and style the same. So I'm going to click on OK. A table of correlation will be generated. Again, the software will correlate the first variable, which is called ordinal, with itself, and then with variable 1, with variable 2, with variable 3. So in this case, as we can see, correlating the variable to itself give a 1 coefficient, correlation coefficient of 1, as itself correlate with itself. If we correlate the ordinal variable
with variable number 1, we can see here that the coefficient is 0.425. So there is a positive correlation, and this correlation is moderate correlation, and it is statistically significant as the p-value is 0.004. So here we can safely and with confidence state that the correlating ordinal with variable 1, the relationship is positive and the coefficient is 0.42, and it is statistically significant, and when there is an increase in the ordinal, there is increase in the variable 1. So it is a positive correlation that's statistically significant. However, if we compare the ordinal to variable number 2, again we get a positive coefficient, which indicate that the relationship is positive. So the increase of the ordinal, increase of the variable, both of them increase together, but the coefficient is very low as it is 0.1, which indicate there is a very weak correlation. However, the p-value is not significant, so the statistical show that the association is not significant as the p-value was 0.4, and our cut-off point for p-value is 0.05. Anything lower than 0.05 statistically significant. Here it's 0.4, so the correlation, there is a weak correlation, but it is not statistically significant. So we can state here that there is a weak correlation between ordinal and variable 2, but the correlation, and it's positive, but it is not statistically significant. When we also correlate the ordinal with variable number 3, we get a coefficient of minus 0.28. This indicates that this relationship is negative, inverse. Ordinal value increase, then the variable score within the variable decrease. So it is a minus relationship, and it is weak relationship. However, if we look at the p-value, find it is really statistically significant, 0.037. So this indicates that the ordinal variable correlate with variable 3 negatively, and either the association or the relationship is statistically significant at a cutoff point of 0.05, because 0.03 is smaller than 0.05. So fairly here we can see that, state that the correlating ordinal with variable 3 is, there is a correlation, that's a negative correlation, and it is statistically significant. Again, if we look also at the column here, we can look at correlation between variable 1 and variable 2. The correlation is 0.08, weak correlation, but not statistically significant. If we correlate variable 1 with variable 3, again the correlation coefficient is very weak, 0.05, close to 0. And the p-value is very, very, very high. So this is not statistically significant correlation between both. Again, if we correlate variable 2 with variable 3, we can see here that the correlation is very weak, positive but very weak, and it's not statistically significant as it is nearly 0.9, close to 1. And if we correlate variable 1 with variable 3, we can see there is a weak correlation that's positive, close to 0, and it's not statistically significant as the value is 0.68. So from this, it is very straightforward to make a conclusion when comparing two variables that are not normally distributed, when the data are not parametric and these data are small, the data on the groups are small, we can compare two variables using the Kendall's correlation coefficient.